Yeah, so welcome to this NSM course on CUDA programming. This is going to be one of the angles that we have not touched since a while now. We have recently have had courses on OpenMP, OpenACC, also on SICL and HIP to target Intel and AMD GPUs. But to target Nvidia GPUs, we have not had specifically CUDA programming course in a while. And Dr. Kingsley Grace has kindly agreed to teach us CUDA programming in this course. So thank you very much, ma'am. She is currently working as an associate professor in the CS department at Sri Ramakrishna Engineering College, Coimbatore. She completed her BE with distinction in CSE from Nurul Islam College of Engineering, Kanyakumari district, and completed ME in CSE from Karunya Institute of Technology and Sciences, Coimbatore. She completed PhD in Anna University in the year 2016. She has awarded NPTEL domain certification on data science in the year 2022. And she has overall 17 years of experience. She has published several papers in various fora. Her research interests include grid and cloud computing, high performance computing, and similar. Um, and her expertise led to funding and consultancy projects from UGC, Nvidia, and Pricol. She has organized and attended various workshops, seminars, and faculty development programs in her area of expertise. She has been recognized as NPTEL translator and translating NPTEL lectures from English to Tamil. She has been awarded NPTEL Discipline Star, NPTEL Motivated Learner for her enthusiastic learning online courses in NPTEL. We are very thankful to Dr. Kingsley Grace for accepting our invite to teach this course, and we look forward to your teaching, ma'am.
Thank you, sir. Uh, Thank you very much. Is my screen is visible, sir?
Yes, it's very much visible.
Okay. So once again, I am very much thankful to NSM Nodal Center for giving me the opportunity to teach CUDA programming. So today, let us see about introduction to GPU. Today, my agenda is what is GPU, what is the difference between CPU and GPU, what are the GPU system architecture, history, and other specific architectures. So already we know that GPU is graphics processing unit. So mainly GPUs are in initial days, GPUs are used for gaming, and nowadays it's for machine learning, video editing, and content creation. So usually GPUs provide high quality gaming experiences, creating lifelike super slick rendering and graphic design, everything. And it is a specialized electronic circuit, so usually used for accelerating videos and creating applications, video applications, and everything. And the primitive GPUs are developed in 1980s, and first complete GPU is developed in mid of 1990s. So usually the GPUs are very highly parallel, highly multi-threaded multiprocessor, and optimized for all type of visual computings. And in real-time visual interaction with computed objects via graphics, images, and videos. And usually, we can say GPU systems are heterogeneous systems because it has to combine with CPU. So all the data we have to transfer via CPU to GPU. The main differences between CPU and GPU are, and in CPU, it handles usually normal processing functions of computer, and then GPUs, already I told, no, it is specific for video rendering and all. So normally the CPU core count of CPUs are almost 64 or 128. So here in GPUs, we are having thousands of cores to execute all the instructions parallelly. So here in CPU, already we know that it's a sequential one, it is GPU is parallel one. And one of the main problem in GPU is latency. But the throughput is very much important than latency. And for data transferring, always we are depending on CPU. So latency is little bit high. But while considering the throughput, the GPUs are better than CPUs. And in huge amount of computations or graphical computations, we require high throughput that we could achieve through GPU. And here in these cases, the latency we couldn't. There is no need to consider latency. And here in GPU, in CPU clusters are available to parallelize the task, but in GPU, most of the times it is data parallelization, and it is extremely parallel. And if while considering image data, so you can parallelly process any type of visual computing applications in highly parallel manner, or we can say it is an extremely parallel one. So we all know that what is the image of CPU and GPU. Anyhow, I have shown that. So here in GPU inputs, we can give the 3D coordinates, texture data, lightning of data, everything. The output from the GPU is the RGB values of each pixel on the screen. Data is sent directly to the buffer display through frame buffer. And in GPU system architecture, so we can see what is the historical PC, what is the contemporary PC with the Intel and AMD CPUs, what is the graphics logical pipeline and basic unified GPU architecture, and what does the processor array look like. So we all know that the historical PC, it consists of VGA for displaying all the images. The display is basically based on VGA. It's a historical PC. Nowadays, most of the computers are having GPUs. And here, Intel and AMD GPU. So here we are having the separate memory for GPU and separate memory for CPU, and all the images are displayed via GPU, and the GPU is connected via the NOR bridge through PCI Express link. Okay, so it's a specialized connector which is connecting the GPU. So normally multi-core CPU and many-core CPU. So here CPU consists of the different processors, and in the GPU it is having the array of processors. Okay. So here in CPU, even though latency is optimized, but we don't get high level of throughput. But in GPU, even though it is having some amount of latency, the throughput is optimized with the help of cores. Okay, we have to remember two names. One is host system, another one is device. The host system means the CPU, the device means the GPU. So the host and the device both are connected with the help of PCI Express bus. So it's a architecture differences between the CPU and GPU. And in the diagram, we are having different ALUs. There are 4 ALUs in the CPU, but here hundreds of ALUs are there. Okay, so 100 of ALUs, and it's connected again via the catches. And the GPU design has different goals compared to those of the CPU. CPU must be good at everything parallel or not. Maybe parallel or may not be parallel. It executes all the tasks sequentially, and GPU assumes that all the workload is highly parallel, where it uses the number of threads for executing the programs parallelly. So in CPU, because of the single thread, the latency is minimized. It consists of bigger caches, and it is having the sophisticated control logic, everything. And it GPU maximize the throughput with the help of threads, and here it is having limited by resources, and lot of resources, registers, everything are available. Multi-threading because of multi-threading, data transferring, it is having the latency, and it also skips some amount of big caches. In CPU, we are having lot of caches, but it is a small amount of caches are available in GPU, and so the sharing is done with the help of control logic among the different threads, and CPU is with the help of execution is speed up with the help of thread. But here, single thread, it is having the multiple threads. So the graphics pipeline is for GPU is having input assembler, vertex shader, geometric shader, setup rasterizer, pixel shader, everything. I didn't go deep into that everything, but in unified GPU architecture, so it does everything is parallelly happens. So some amount of history of GPU. So before 90s, there is no GPU. We are having only VGA cards. After that, slowly the GPU implementation happens because of high demand of gaming and visual analytics, everything. And in 1999, GPUs implemented full graphics pipeline. And again, the first GPU is released in 99, and programmable pipelines, that is Nvidia GeForce 3, released in 2000. By 2007, the Compute Unified Device Architecture is established. Okay, CUDA. So it is API used for programming in GPUs. And in 2010, general purpose, that is GPUs for non-graphical compute intensive applications. So NVIDIA has developed with the help of CUDA architecture. So afterwards, there are different n number of GPUs are developed by different companies. So also we can say the GPUs, we can say it is a video processing unit. Okay, the other name for us, because mainly the GPUs are used for video processing, and the GPU was given name was given by Nvidia in 99 because of releasing the first one. And already I told you the GPUs are mainly for data parallelism, and the CPUs is only for task parallelism. So here the video RAMs are used in GPUs, but the external RAMs are used in CPUs. The video RAMs are very fast but very small in size. Here the low cache memory, already I told it is having high cache memory. So these are all some of the, already told some of the history, how the evolution happens in GPUs. So here in this 99, after 99, there are n different number of GPUs in different names. NVIDIA has released in 2000, for example, 2009 Fermi GPU. We can use it for OpenCL. 2012, it is having Kepler GPUs, Kepler K series. After that, 2014, it is having Maxwell GPUs. So why we are going with GPUs? Okay, so here in this diagram explains. So using GPUs, we can achieve the speeds in gigaflops. And with the help of GPU, we can execute single precision data, that is floating point data, and double precision data. Single precision data in the sense 30 bits, and double precision in the sense 64 bits. So here, look into this diagram. So while using CPU single precision, the speed is very low. But while using the GPUs for both single precision and double precision, so the speed is very high. Okay, so that's why in most of the HPC applications, the GPU takes an important place. So again, another one diagram. It explains what about the GeForce graphics card, what about the Tesla graphics card, what about the Kepler graphics card having the speeds. So again, one more thing is, while increasing the number of transistor in the VLSI design, so the size of the GPUs also reduce a lot. Okay, so this is a theoretical speak of floating point operation per clock cycle for single precision for different GPUs. For Intel, for Nvidia GeForce or AMD, Intel Xeon, okay, different GPUs are available. So in most of the cases, almost the latest GPUs provides the speed as per same while considering. So this diagram explains while year by year, NVIDIA has developed different applications with the help of GPUs. Most of them are visual computing applications. For example, lung cancer detection, they have developed some application and Clara. So there are different applications have been developed. So in accelerating HPC, so we need high performance computing in molecular dynamics, physics, engineering, and geosciences. So there are different applications have been developed for each and every area. So the speed up is very high. So for 1.0x speed up for NVIDIA V100, so this is increased a lot for while using the A100 GPUs. So these are all the some of the different architecture or some of the different GPUs released or developed by NVIDIA. 2011 Kepler and 2015 M series, P series. So in 2023 they are having L series. So all the names of the GPUs are the famous scientist names. So we all know the flying taxonomy of CPU architectures. So proposed in 1996. So it based upon SISD, MISD, SIMD, and MAMD. So this is a Flames taxonomy. The in GPU architectures, the Flames definition is not fit. GPUs are not fit into Flames definition. So because of its architectural designs, mainly the GPUs are either SIMT or hardware multi-threading. SIMT means single instruction multiple thread. Only one instruction may be executed in multiple threads. So main thing is the hardware will provide the divergence automatically in this SIMT. So in hardware multi-threading, we are having hardware resource allocation, hardware thread scheduling, and hardware lays on threads to hide latency. So the main thing here is, so we are not writing the program, parallel programs for GPUs. So all the parallelization is done with the help of hardware, which is hidden to the users. So and also the context switching is free there in GPUs. Okay. So in some of the next we see some of the GPUs there in Nvidia in the 2006 the GeForce GPUs have developed. It is based on GAT architecture. So it supports C programs for allowing code that could be run in GPU, and it replaces all the separate vertex and pixel shaders by planing. So because of single unified processor, so either executes shaders or computing programs. So it also introduced a scalar thread processor, eliminating the need for programmer manually manage and vector register. We couldn't, there is no need for the programmers could needs to manage the registers and everything. You simply write the code, and with the help of some small amount of code, and everything is managed by the hardware. It starts from the GeForce 8000 GPUs, and it also introduces a single instruction multiple thread execution model, and it also introduced shared memory and barrier synchronization for inter-thread communication. So in 2008, they revised the GAT architecture. So the second generation of unified architecture is released, that is GT200. So here the number of streaming processor cores are increased from 128 to 240. The previous one it is having only 128. So the next series it is having 240. Nowadays it is having thousands of cores, and the processor is almost double here in GT series, and The only important thing here is the memory coherency. So what happens is if there is any free memory, that will be combined and used by the GPU automatically. There is nothing could be done by the programmers. And also the double precision support is included. So it is mainly used for the high performance computing applications. So actually, already I have shown this diagram. So this is a conceptual view of the GPU. So already I told it is having an array of streaming multiprocessor and which supports the concurrent threads, and each SM is having set of processor, and at each clock cycle the multiprocessor executes the same instruction on a group of threads. Okay, it is called as wrap. Okay, so one single instruction is executed by different processors. It is one visualization of streaming multiprocessor. It is having the multiprocessor 1 to n. So one single instruction is given to the number of multiprocessor. So the number of multiprocessors are available in a single device. So this is another one architecture. So it is having the all the multiprocessors are sharing the same memory. So the data sharing is very easy here. And here the device memory, it can all the processor can access the data from the device memory, sorry. So this is a processing flow of GPU. So GPU does not have the access to main memory. Okay, in future it may be changed, but initially it won't have any main memory like our CPUs. And so in each and every time while executing any programs on the GPU, we have to copy the data from CPU to GPU memory. So which has to be done by the CPU. And this movement is the highest cost. We can say it is a latency, and all the things from the CPU memory through PCIe bugs, the data is moved to the dynamic RAM of GPU. And this is the execution flow. So through CPU, the code has to be sent to the GPU, and the thread, all the threads which needed to execute that particular program will be enabled. So once all the executions are completed, so the results will be stored in the right side, which is GPU. So that will be transferred to the CPU memory via the same bus. Sorry. So at last, we can say the GPU consists of two components. One, global memory. So all the streaming processor can access the global memory, and it is having the streaming multiprocessor. Each and every streaming multiprocessor having their control units, register, execution pipeline, caches, and everything. And GPU memory is accessible by the GPU and the CPU. Okay, GPU can directly access the memory. Sorry. So next we'll see something about what are the market of GPU. So it's very high according to President's research. It's very high, 773.07, because lot of HPC applications are nowadays developed. And here also another one research says 2030 it made $28.7 billion. And this is another one survey. So nowadays we can get the GPUs via GPU as a service. Okay. So we'll see while doing the programs. It's again one more thing. Okay. So while doing programming, so I'll give you a little bit hint about how to program using GPU. So I think you can able to see my screen. Are you able to see my screen?
Yes, madam.
Okay, okay, thank you. So we'll be doing programming using Colab. Okay, you know how to open the Colab. So I'll give a little bit hint about how to do programming, everything. So we'll have a details session tomorrow. And after opening, you all, some people may know that. So you can go to runtime and change runtime type. You can change the runtime type to from CPU to GPU, any one of the GPU. So T4 GPU, this only enabled for me. Then save this. And in initial days, the executing CUDA C programs in GPU is very difficult. But nowadays it's very easy. So if you give this ls command, you can see the CUDA 11.8 version is installed here. You simply give and execute. You can say that you can see that CUDA 11.8 is available. And the same thing we can do it in Linux also. And where it is while executing CUDA programs. Okay, so here we are using Nvidia GPU. So we are having NVCC, that Nvidia C compiler is available. So you can just simply give which NVCC. So that will give you the location where the NVCC compiler is installed. And we can also see the version of the NVCC compiler. So with this copyright information and everything, and release 11.8, because we are having CUDA 11.8 here, the same thing as here. So the CUDA 11.8 version is available. And one more thing is how many GPUs are available. We can also see that with the help of this command. Already I have executed all those things. That's why again I'm executing it. It immediately executes. Otherwise, it will take some 1 or 2 seconds. So the first line says that NVIDIA 0. So we have selected only one GPU, in runtime. So only one GPU is there. So if any systems which are having more than one GPU, that will be shown NVIDIA 0, NVIDIA 1, like that. 1, 2, etc. And one more command is there, that is NVIDIA SMI. So it will provide the detailed information about what is the processor, what are the other things available in NVIDIA. That is SMI means System Management Interface. So if you have given this, so T4, already we have seen, no, the T4 GPU is available here. And CUDA version 12.0, and here it is 11.8, it is also known as 12, that is 12.0, whatever the driver version, and GPU name. So the thing in NVIDIA 0 port, it is available. The name is Tesla T4. Persistence name is off. Fan not applicable. Temperature. So all those things are displayed here. See, if you have used the same thing in your laptops or other workstations, you could see all the information available in the uh, what is called uh, all the GPU information available in your device. And here I have written one small program, the C program. That's all. So here, while writing programs, what you have to do is you have to give um, that is what is it, percentage symbol. Okay, double percentage symbol, write file, your file name dot .cu. Okay, so we'll have a detailed session on how to write the program and how the process flow happens tomorrow. Anyhow, I'll give some more time is available. I will give a small hint about what is happening here. So you give write file and file name .cu. So I have simply imported the stdio.h for printf scanner statements. So simply I have written one program, printf hello world from CPU. Okay, a very small hello world program in C, but I have saved in .cu extension. So it will give writing the file in this extension. So then we are having one simple command. While executing in Linux, you can give in like our C program execution. So here you give NVCC. So NVCC, after that, you have to give what is the file name -0. That is in which file the output has to be written. Everything is same. So here you have to give some of the that is SM and generate code, all those things in additionally. So you simply execute, some warning message comes, you simply omit that warning message. So our output is written here in first C. So execute that one. So it will print what is there in the printf statement. Okay. So what happens here is, uh, do you know where it is executed? So I have written the program in first.cu. I have stored in the name of CUDA program, but I have executed. I have got the results. So because the NVCC is the extension of C program, C compiler. NVCC is the extension of C compiler. You can run the C program using NVCC too. Here it is executed in CPU alone. It won't transfer any data to GPU. It's simply executed in the GPU. Because I didn't tell any statement for transferring data to data from CPU to GPU. So here the main thing is while writing CUDA programs, you have to consider some 2 or 3 things. The first one is uh, what are the operation has to be executed. You have to write it as a separate function. So that is usually called the kernel program. Usually the kernel programs are executed in the GPUs, and all the other statements we are writing inside the main function are executed in the CPUs. Only the kernel programs are executed in GPU. So here I am writing only the statements within the main function. I didn't write any kernel program. If I have written the kernel program, then only that will be transferred by the CPU to GPU. Otherwise, it will be executed in the GPU. So here it is executed in GPU. The first one is we have to write the kernel program. What are the operations we have to execute in the GPU? So then we have to uh, uh, we need 2 sets of variables. Okay, one set of variables for storing data in CPU and another one set of variables for storing data to GPU. Okay, so what are the variables you have to move from CPU to GPU? That will be done with the help of CPU. Once the calculation is over, then that will be transferred by the CPU from GPU. Then we can display it in your CPU display. Okay, so these are the 3 steps we have to consider while writing any CUDA programs. So this is again the same version of the first one. So here what I have written is hello1.cu, again the hello world program Hello. And here in this particular program, I have written the kernel. This is called the kernel program. Usually the kernel program is written as global function. And you can give any name here. Here I have given the name as a kernel. You can give any name. So here again, I am printing CPU hello. So the kernel is called 1 comma 1. Okay, the kernel function is called here 1 comma 1. This means the number of blocks and number of threads. Usually, already I told you, so there are n number of streaming multiprocessors are available in GPU. Again, we are having lot of threads there. So how many threads you needed, you can specify it here. How many blocks needed, you can specify it here. So based on your data size and your program nature, you can give the number of blocks and number of threads. So here, the kernel function is an empty function. I didn't give any statement here. Simply I defined that kernel definition is available. And in the main function, what I do here is I have called the kernel function with one block and one thread. Okay, again it is empty. So next I am printing CPU hello. So it returned. And what happens here is the GPU is called, some control is transferred there, but there is no statement. It automatically returned back and the hello is printed from the CPU. Okay. So any doubt? So tomorrow I will try to send the codes via the chat. Today I couldn't do. So if possible, I'll try. Yeah, chat is available. See, if anybody want to try, you can try. If you have connected using your laptop, else you can do. Can you able to see my messages?
Yes, ma'am.
Okay. So if anybody is connected via your laptops or something else, try this and tell what happens. Are you getting some results? Just give some message. Sorry. This is a command to execute. So if you are executing in some Linux machines, there is no need to give this double percentage symbol and everything. So you simply write the program in your editor and save it with the help of .cu extension, and with the help of NVCC, you can simply execute. That's all. So anyone is executing? No? So I'll give some 2 or 3 minutes. You try to execute. Okay, okay, good. The next one is yeah, actually, in local Jupyter notebook, I think it won't be executed because we are using some GPUs in on cloud. So we need some cloud while running uh, CUDA programs. Oh, okay, okay, okay. So for if you're having the Nvidia GPU and CUDA installed, so there is some different procedure you have to follow. So I didn't try the what is called this this thing in my local. I'm also having the GPU in my laptop, but I didn't try it using the Jupyter notebook for locally. If possible, I'll try and I'll tell. So you can do one thing. You store the program in some other way, and through command prompt you can execute. So usually in workstation we do like that only. If possible, I don't think I can able to do because I didn't try it previously. Yeah, yeah. So I'll explain. So usually, what we have done here is some we have written one kernel function for executing uh, any some here in this program we are executing some empty function. So the GPU is enabled and called by the CPU. Okay, once it is done, normally what the reset will do, it will come to the initial position. No, so the CUDA device reset means something happens in the GPU. After that, you reset the GPU and it comes to the initial position, initial condition. That's all. It's not a big command like. So it's simply you are resetting the CUDA device, that is GPU. That's all. Yes, correct only. So you can change the flags, otherwise it will show some warning. But I couldn't find what about the flags for that GPU available in the Colab. That's why simply I am giving the same command. Okay, anybody else executed the program? Okay, good. Okay, in today's sessions, we have seen some introduction about GPU and what are the differences between GPU and CPU, and uh, some simple program and how to execute it there in Colab. So one more person is asking CUDA Fortran. So in at last, I didn't executed any Fortran programs. I have executed Python programs. So once the C programs completed, time permits, I will show how the Python programs could be executed in CUDA. Okay, thank you. We'll see you tomorrow at the same time with more CUDA programs.